Hello students, it's Dr. Marks and our topic for today is combinations and permutations. I think this topic's kind of fun, so I hope you do too. Let's get started. Now, when we're talking about this particular topic, it's with the idea that sometimes we want to be able to count the number of possibilities. So if we just had some combinations of things and we wanted to know how many possible combinations, we need a way to calculate that. For example, maybe we're assigning 5 people from your firm to a committee. And so it can be any set of 5 people, and we want to know how many different possibilities are there. Well, if we're running a lottery, by the same logic, we might be asking how many different combinations of numbers can be generated in terms of lottery outcomes. Well, for both of these questions, whether we want to know how many combinations of 5 people could I have if I want a committee of 5, or how many different combinations of numbers can be generated in a lottery type situation, to do that, we need to use combinations and permutations. So that's our topic for this lecture. Now, let's begin by asking the question, how are combinations and permutations different? And the answer is that it depends on whether order matters. So if order does matter, we need one. If order doesn't matter, then we need the other. Like, for example, in a lottery. Now we know in a lottery we need to match the numbers, right? When they draw the numbers, we need to match them. But for most of the lotteries I've seen, we don't need to match them in order. We just need to select the right numbers. We don't have to select them in the same order. So that's a combination. Combinations are a sequence of outcomes where order does not matter. So do I match the lottery numbers? It doesn't matter if I match them in the order they're called out. So combinations are simply a way to count the possibilities. For example, let's take an easy example. Let's say we're wondering about the composition of gender of kids in a family of 4, and we want to know what are the possible combinations, and I think I mean 4 kids here. What are the possible combinations of gender of kids? And with a combination, order doesn't matter. So if we don't care which came first, which came second, which came third, which came fourth, whether boy or girl, then we're using a combination. For example, let's use as our concrete example drawing cards from a deck in poker. And let's say it doesn't matter what order they're handed out. So if it doesn't matter what order they're handed out, then do you agree we can have 2 equivalent hands but in different orders, like this and this? So do we agree? Both have an ace, both have a 5, both have a 7, both have a 10, both have a king. But they are in different order. But for combinations, these would be treated as the same, because with combinations the order doesn't matter. We just want to know how many different combinations of 5 cards could there be. Now, to calculate the number of combinations, we have to have a set with n elements. So the total number of elements in the set is n. That's going to be the terminology that we use. Total number of options is elements, and we're going to indicate it as n. But then we want to find combinations of size r. So for example, if we're drawing 5 cards, 5 is my R, from a deck of 52, then 52 is my N. So I have 52 elements in a deck of cards, and when we draw 5 cards, we're finding combinations of size R, R equals 5. And then we have a fairly messy calculation using this equation right here. Now, you might be looking at those exclamation points saying, I don't really know what that means in an equation. So let's cover that first, because chances are we don't remember much about this, but I'm expecting most of you did this somewhere in your college career. So the exclamation point stands for factorial. That is indicating a factorial. And I've given you an example right here in the yellow box. 4 exclamation point is going to be 4 multiplied by 3 multiplied by 2 multiplied by 1. So 4 multiplied by every number below it. And that equals 24. So 4 factorial is 24. N factorial is going to be equal to n times n minus 1. All right? But on and on and on and on. You get the idea. So how many different combinations of 5 cards can be drawn from a 52 card deck? Well, we know our N, 52. We know our R, it's 5. So using our equation, we can plug in here for N and for R. So we want the combination of 52 and 5. The numerator is going to be the number of elements, 52 factorial divided by 5 factorial multiplied by 52 minus 5 factorial. So gang, once we've determined our N and our R, plugging into the combinations equation is pretty easy, with the exception that I wouldn't want to calculate this by hand. And luckily we're not going to have to. We'll talk more about that in a minute. But if I do the math here, we're going to end up with 2,598,960. So there's more than 2.5 million combinations of 5 cards that can be drawn from a 52 card deck. That's pretty amazing. Now, as I just said, we don't want to sit at the calculator and do 52 factorial, right? 52 times 51 times 50, it'd be on, and I would keep making mistakes, and I'd be starting over. It would take me all day. So we can use an Excel function, and that Excel function is fact for factorial. So if I wanted to know the factorial of a number, I can just use fact and then tell it which cell I want the factorial of. So if you look at this example right here, we're taking the factorial of cell B5. Well, if you look at cell B5, then you've got 8. So 8 factorial must be 40,320. So I'm not going to ask you to do this longhand, except for maybe if there was a really simple calculation. You know, we could easily calculate 5 factorial on our calculator. But for big things, we don't want to spend all our time. Let's talk about Powerball or the Mega Millions lottery. Maybe some of you are actually in this industry. Maybe some of you own a store where you sell either Powerball or Mega Million lottery tickets. So with these games right here, you need to have the right numbers, but you don't have to pick them in the right order. So 11, 29, 57, 82, and 14 means you would win if you pulled and chose 29, 14, 57, 82, 11, right? We all understand what I mean when I say order doesn't matter. You have the right numbers, different order, you're a winner. Awesome. So we can compute how many different combinations there are in this Powerball or Mega Millions lottery game. And then once we have those combinations or the number of combinations, we can compute the probability of winning. So while the idea of combinations and permutations is kind of a little bit of a spin-off of probability, it certainly connects to the topic. So let's look at Mega Millions. And I had to look this up. I've not played Mega Millions, but I learned that there's an easy pick option. And in that easy pick option, you have to match 6 numbers out of 70. And I'm assuming there's just 1 through 70. So we want to ask ourselves, how many different possible combinations are there going to be? And that will help us determine the probability of winning. So how many combinations are there? Well, we need to use our equation. So here's our equation for combinations. And let's review. What's N? Number of elements, that's 70. What's R? The combination size, 6 numbers. So we can plug in our 70s and our 6s and take the factorials, but we're starting with this equation right here. So when I start with this equation, I'm just going to reduce the denominator. 70 minus 6 is 64, so I've got 70 factorial divided by 6 factorial multiplied by 64 factorial, right? That's too much math, but if I found a way to do this easily, which there is a way because I just showed you on Excel, that we can have Excel calculate the factorials for us, and then we can even ask Excel to calculate this for us, but we get 131,115,985 combinations. I've had trouble even getting that out, right? Because that's so staggeringly large, right? That tells us that the probability of winning is pretty small, am I right? Now, let me let you in on a little secret, and that is online there are calculators that will do this for you. So I actually cheated. I didn't even go to Excel, so I'm not going to lie. I went to this calculator.net and selected permutations and combinations calculator, which you can see the whole website there at the bottom, but I think if you just put in permutation and combination calculator, you're going to find this or one just like it. So if you look on the right hand side, you see that calculator.net, in this part of its calculator, will give me both permutations and combinations. Right now we're just looking at combinations, which is the bottom number that I have in red. And so I didn't do any of this math, and I didn't even program it in Excel. So there are ways to do this far more easily. Now, back to the question about selecting a committee from people in your firm. How many ways can you select a committee of 4 people from the 80 people who work at your firm? So we want to know how many different combinations are there, right? And we all agree order doesn't really matter, right? Do I care about the order of choosing 4 people? No. So it seems like combination is the way I want to think about this. Just want the total number of possibilities. So we've got our equation again, and we know that N is 80. It's the total number of options. R is the size of the combinations. We're going to have 4 people. So 80 factorial divided by 4 factorial multiplied by 80 minus 4 factorial. Well, plug it into your combinations calculator or in Excel, and you get that there's 1,581,580 different combinations. So, that's interesting. And I'm sure you can think about places where this could be relevant in your actual career. But I could see definitely lots of applications in mine at a university where maybe we want to randomly select committee members for things. All right, moving on. Now, we just finished talking about combinations. There's something that's similar with one small tweak, and that is the permutation. In some cases, do we agree that order does matter? Not always, but sometimes order matters. And if it does, then we're working with permutations. So a permutation is an ordered arrangement of the elements of some set S. All right. That sounds really formal, but we're basically just saying it's like a combination, but in this case, order matters. So let's let our set S equal the numbers 1, 2, 3. So if we're talking about permutations of this set of numbers, do you agree that it could be 1, 2, 3? It could be 2, 3, 1, it could be 3, 1, 2, etc. Because order matters. Well, if I asked you to figure out how many different possibilities there are, well, I don't see 2, 1, 3, right? So I'd have to figure out all the possible combinations that take into account order. And it turns out there are 6 possible permutations of these 3 numbers. So again, permutation, order matters. 1, 2, 3 is not the same as 2, 3, 1. Make sure you understand with combinations, 1, 2, 3, 2, 3, 1, 3, 1, 2, 2, they would all be the same thing if we were talking about combinations. Now to calculate permutations, we have another equation, and it's slightly different than our calculation for combinations, obviously, because we're doing something different, but it's still an easy calculation. We know that n is the number of things in the set, and r is the size of the groupings, right? So back to my set of 1, 2, 3. What is n for this? Do we all agree that n is equal to 3? Yes. N equals 3. That's the number of elements in the set. And what is r? Well, r is also 3 because we're choosing 3 numbers. So we want to know, for this set of 3 elements, how many possible combinations of 3 could we have if we care about order? So let's plug this into our equation. This one's easy for us to figure out ourselves. And we get 3 factorial divided by 3 minus 3 factorial. Now you're probably scratching your head and saying, wait a minute, that's 0. All right, give me a second. 3 factorial over 0 factorial equals 6. And I hope you're thinking, well, how can that be 0 factorial? What is that? Well, 0 factorial turns out to be equal to 1. So I have 3 factorial divided by 1, right? And so I just have 3 factorial. 3 times 2 times 1 gives me 6. So that's how we get the answer 6. But you do need to make a mental note that 0 factorial is not 0, it is 1. So back to our example of a lottery. Let's say that we need to have the right numbers, but also you have to pick it in the right order. Now I realize this is probably not how any lotteries work, but just go with me on this, okay? So let's let there be 70 numbers, just like we looked at before, and you're picking 6. Do you see where I'm going with this? It's the same example that we looked at before with the combinations. But now I need permutations, not combinations. Why is that? Because order matters. Remember, in the example we did before, you just had to pick the right numbers and no one cared about the order. But now you have to pick the right 6 numbers and you have to pick them in the right order. I hope you're seeing that, yeah, that's a much harder thing to win on, right? Much harder thing to win. So we want to know how many different possibilities are there. So let's go back to our permutation and combination calculator and let it do the work for us. Now, when we plug in selecting 6 out of 70, but order matters, now look at our number of possibilities. Because order matters, we've got, what is that, 94,403,509,200. Wow. And that's certainly a whole lot more than our combinations. So I hope you see that when we went from combinations to permutations, well, we had a whole lot more different choices, right? So one thing I want to remind you, as it says in the yellow note, there are over 94 billion possible outcomes when order matters, because remember, it's kind of like we're double counting, right? 1, 2, 3 is not the same as 2, 3, 1. So we have to count all the 1, 2, 3s, the 2, 3, 1s, the 3, 1, 2s, the 1, 3, 2. Whereas in combinations, we didn't count those separately. So what has happened to the odds of winning if order matters? What has happened to the odds of winning? If order mattered in our lottery, do you agree that the odds of winning have gone down? And not just down a little bit, right? They went from 1 out of 131-ish million to 1 out of 94 something billion, right? So your odds have gone way, 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 way down if order were to matter. So the second question in yellow says, hey, to get people to play then, what would have to happen to the payoffs? If order really mattered, are people going to play this? No, not unless the payoffs get much, 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 much bigger, because the probability of winning has now gotten even smaller, right? And it's hard to win the lottery, but it would be incredibly hard to win a lottery where order mattered. Now let's go back and do some comparisons. So we've got our combinations and our permutations. Remember, combinations, order does not matter. Permutations, order does matter. And we see a slightly different equation. But look at that, guys. It only differs in the denominator, right? It only differs in the denominator. On the left, we see an extra r factorial. So based on these equations, guys, which will be larger? Now, we already know the answer because we just did an example. But just based on the equations, you should be able to tell me which is larger. And my hint is, look at the denominator. Look at the denominator. Well, with combinations, we have a larger denominator, right? Because we're taking the thing in the bracket, n minus r factorial, and we're multiplying it by another number. So dividing by a bigger number. Think about it. When we divide by a bigger number on the bottom of a fraction, what happens? Our answer gets smaller. Think about it. 1/2 versus 1/5. Which is smaller? 1/5. As the denominator gets bigger, the fraction gets smaller, right? The calculation gets smaller. So remember, why is it that there are fewer outcomes with combinations? Because again, ABC and BCA are the same. We only count it once. But remember, with our permutation, first of all, you see we're dividing through by a smaller number. When we divide by a smaller number, our answer is going to be bigger. And it's going to be bigger because ABC and CBA and BCA and all those different possibilities of order, they are not the same, and each now has to count. So hopefully you have a good intuitive feel for why permutations, when order mattered, we had so many different possibilities, right? It was in the billions. But with combinations, we had a significantly smaller number of possibilities because order doesn't matter. So I don't count the same thing, ABC, BCA. That would be 2 for permutations. It would only be 1 for combinations. Let's summarize, guys. As we just said, combinations are a sequence of outcomes where order does not matter. But for permutations, that's a sequence of outcomes where order does matter. So if I give you a problem, you need to ask yourself the question, okay, does order matter or not? What is the question asking? Both are ways to count the possibilities, but as we showed, they have slightly different equations, but they only differ in the denominator. And that makes it easy to know which should result in more possibilities. Now, gang, remember, we have online calculators that will calculate these things for us, and Excel also can calculate a factorial as well. Let me know if you have any questions, guys. Thanks for listening, and I hope you have a fantastic day.